Good evening everyone. This is Srilata. Today we are going to discuss about a configurable computing machines for software radio handsets. We use configurable computing machines for software defined radio handsets. With the emergency of third generation, we are beginning to see an acceptance of SDR concept. Third generation standards support adaptive modulation, coding and controlled quality services. Cooperative networking is a powerful concept that enables the radio to provide additional services to the user by interfacing with neighboring devices and networks for resource sharing. Software radio began to obtain popularity largely in base stations but not in handsets. One of the most efficient software radio implementation can be obtained by reconfiguring hardware to the current algorithm while storing other waveforms in memory. It leaves a power saving. DSPs have excellent programmability, but today's DSP alone cannot handle the complex algorithm at the required speed with reasonable power consumption, while a combination of FPGAs and DSPs can handle most waveforms. Now, let us see the CCMS in handsets. An optimal software radio solution should be able to tune its hardware to the needs of the current system, thereby minimizing power and silicon area to achieve performance similar to SiC implementations. Whereas DSPs and FPGAs provide different level of reconfigurability and aid in implementing flexible design. CCM architecture allow dynamic hardware reconfiguration with maximum flexibility or reviewed and assessed. This is followed by design recommendation of CCM architecture for use in software radio handsets. CCM implementation gives the designer the option to selectively speed up algorithm to developing specialized cores. Figure 1 here, this figure shows two possible implementation of a finite impulse response filter on a CCM. Here, figure 1A requires n plus 2 plus L by n minus 1 cycles to compute each output. And if we consider n is equal to 16 and L is equal to 256, then we will get 16 plus 2 plus 256 by 16 minus 1. It means 33 cycles to compute each output. And if you see the figure B, like B requires n plus 2 plus L by n minus 1 clock cycles to compute each output. If we consider, figure 1B requires log 2 into 2n plus 1 plus L by 2n minus 1. It means if you consider 2n is equal to 16 and L is equal to 256, we will get 20. Means we need 20 cycles to compute each output. Now, let us see the graph. Combining a processor with a reconfigurable computing array. One of the most significant features of graph is the high-level compiler that can extract instructions from C code and implement section of code automatically with high instrument level parallelism, ILP. And now, today's general purpose processors are highly optimized for executing complex sequence of instructions for a popular set of basic operations. The focus of graph research is the integration of a reconfigurable computing unit with an ordinary RISC processor to form a single combined processor chip. Gate array is organized as 32 row bits by 23 columns of 2-bit logic block. A 24 column of control block manages communication outside the array. Each logic block takes as many as 4 2-bit input and produces up to 2 2-bit outputs. Each logic block includes 4 bits of data state totaling to 92 bits per row. Partial configuration of an array is possible in row increment. Up to 128 bits per cycle memory bandwidth to any 4 rows in the array. Reconfigurable array can perform data cache or memory access independent of the MIPS core. Control synchronization between the MIPS core and the reconfigurable array is flexible and efficient. Now, my friend Monica is going to continue the next topic.
Well, hi, I'm Monica. Till now, my friend Srilata explained about the academic research efforts. The first one is GAT, and now let me continue the second one, which is nothing but algorithm specific instruction set processor, simply ASIP. Breckenseck proposed an approach in which similarities and differences between the waveform standards are identified. To overcome this issue practically, they moved away from the ideal software radio where a single hardware device is reconfigured to any standard. Instead of this, the software reconfigurable radio uses a little standard specific hardware to implement more waveforms. This architecture is an independent reconfigurable hardware accelerator that can be used by the DSP or microprocessor. The main goal is to allow the DSP to perform complex high-speed processing on the ASIP. The ASIP itself may consist of one or more processing elements, where each processing element can be designed for a particular class of algorithms, for example, linear transformations and orthogonal transformations. Any system can contain one or more processing elements of a similar kind based on the needs of the system. The ASIP can be used to implement subroutines or loops that can run without interruption from the main processor. Once the processing is completed, the ASIP interrupts the main processor and the data is transferred to DMA. However, unlike GAD, the reconfigurable sections are specialized for certain algorithms, which allows optimization of the reconfigurable sections for wireless applications. Now let's see about the next architecture, which is nothing but field programmable functional array. It was designed at University of Twente, Netherlands. Researchers proposed a heterogeneous reconfiguration architecture along with a QoS driven operating system for future low power mobile multimedia systems. This heterogeneous system on chip consists of a general purpose processor, a bit level reconfigurable processor, and several word level reconfigurable modules, which are nothing but field programmable function arrays, tiles. These are called as tiles. Each of these modules is targeted for specific applications with programmable runtime reconfiguration capabilities. This architecture is based on replicating a simple processing element, each with its own instruction stream. Therefore, the aim is to keep each processing element small enough to maximize the number of processing elements that can fit on a chip. This improves the chip's clock speed, energy consumption, and the amount of parallelism it can exploit. The FPFE consists of interconnected processor tiles where multiple processes can run in parallel on different tiles. The figure shows an FPFE with 25 tiles where each tile has 5 arithmetic logic units. The arithmetic logic units on a processor tile are tightly interconnected and are designed to execute the inner loops of an application. This was programmed using the locality of reference principle, which assumes that within a loop of a program, there is a high probability subsequent instructions. This architecture shows that reconfigurable hardware with processing elements can be used as a solution for future handsets. The interconnections between the tiles and the composition of the tiles, however, needs to be optimized for specific types of communications applications. Next comes the RAW. MIT University designed this architecture, RAW microprocessor. RAW microprocessor has 16 identical programmable tiles. Each tile consists of its specific element. Each tile connects only to its 4 neighbors. This architecture exposes the interconnection between computational units inside a microprocessor to the instruction set. The instruction set architecture is designed to indicate to the programmer where the instruction would be physically executed and the number of hops between tiles necessary for the operation. This allows the programmer to control the data transfer between tiles as shown in the ASIC. This architecture enables runtime software control of hardware configurations, which is desirable for software radios. However, the microprocessor architecture has to be designed to minimize power consumption as well as programming overhead. The next will be continued by my friend.
Hello everyone, let's learn something new about CCM Stallion and its architecture. Recently, the Configurable Computing Lab at Virginia Tech has developed a new breed of processors termed CCM, which is known as custom computing machines, which holds great promise as a processing solution in the handheld domain. Here, in Virginia Tech's scalable CCM Stallion, it is specifically suited for flexible, high-throughput, low-power computation, which is based on stream-based processing. In the stream-based processing, it uses a common port for both data packets and programming packets. Stream-based processing. What exactly is this SBP? It explains the concept of pipelining by allowing the pipeline to operate on a continuous stream of packets. This stream of packets contain header that indicates the nature of the stream packet and also the next module, where the subsequent programming packet should be forwarded. Therefore, each programming stream is independent and self-steering. Coming to the stream-based processing element, here each element in the stream is capable of interpreting the packet to determine whether to process the packet or to use the packet for configuration or to leave the packet unchanged. As a result, the element then constructs packets for the next element in the pipeline. To support these changes in configuration and for more advanced processing, each processing element also should have dedicated memory. Coming to the Stallion architecture, as you can see in the figure, it consists of two meshes of 8x4 interconnected functional units, and the multiplayers are connected by a crossbar network of flags and buses. And here Stallion has 6 ports that can be dynamically programmed to either input or output data ports. And from these data ports, the stream proceeds through the crossbar and then to either mesh of functional units. After being processed in the functional unit, the stream can continue through the mesh and go back through the crossbar to any part of the chip or off the chip via data port. Output of this functional unit can be routed logically to adjacent functional units or to multipliers located on the Stallion through the crossbar or skip buses. Finally, each functional unit is capable of generating and processing an array of flags, which can be used to control and monitor the functional unit's operation. Though Stallion was not designed specifically for low power wireless communications, but the concept of stream-based processing is ideally suited for handheld CCM architectures. Here, SBP is combined with wormhole reconfigurable computing, which allows algorithms to be efficiently paged in and out of the chip. As you can see in the figure, in this wormhole reconfigurable computing concept, stream packets indicate next module, and therefore SBP is based on wormhole reconfigurable computing, which makes use of data paths and which greatly simplifies the implementation of multi-mode systems. Coming to the challenges and design issues for CCMs, here CCM offers many features that make them extremely desirable in handsets. Especially in this wireless industry, there is a lack of sophisticated high-level design tools and the compilers that ease the burden on the designer. Among all these, ease of programming is an important characteristic in the hardware. In the high-level languages similar to C, Java, and MATLAB, VHDL, the ability to program the CCM is easy makes it easy for developers for incorporating CCMs in their designs, but this places a great burden on the CCM compilers. Coming to the design issues, CCM is designed as a separate chip that interfaces to a DSP, which requires careful design of the input-output bandwidth. If the transferring of the data is directly onto the CCM, it's not a feasible option. But if we use a separate CCM memory banks as a means of getting data in and out of the chip, then it could be a possible solution. Coming to the conclusion, here the main goal of our article is to examine the applicability of CCM to the handheld domains, and also to figure out how a CCM solution compares to traditional devices and an ideal handheld solution. Therefore, software radio handsets require extremely flexible and efficient low power hardware. Thank you very much.